Now we'll look at a couple of examples of proving an expression is true for all values of n. We'll prove two different expressions are true using the mathematical induction principle. But first we'll motivate it a little bit. The story goes that Friedrich Gauss, who was born in 1777 in Germany, he was punished as a child in school, in elementary school, and the entire class was asked to, for punishment, add up the first 100 positive integers and come up with that sum. So 1 plus 2 up to 100. The rumor is that, or the story goes, that he came up with a solution in seconds. And so adding all these numbers up, the approach he took was S, the sum, is equal to 1 plus 2 plus plus 99 plus 100. And then he wrote it again. And he did it in reverse order. Two plus 1. And then he has two equations, and equations are allowed to be added to get a third equation. So he added this up and got 2s is equal to, and he added up all of these columns, which all add up to 101. And he had 100 such numbers. So he said that 2s is equal to 100 times 101. And I guess I got ahead of myself. Dividing both sides by 2, he got this, which is 5050. So in a matter of seconds, he was able to come up with that sum using a little trick. Now, we're going to prove our first example, as is usually the first example you see in any class that does proofs by induction. We're going to prove that this holds for any integer n, that this similar formula will hold for adding up the first n integers. So notice, it's worth noting that the principle of mathematical induction does not come up with the formulas. If you're given a formula, you can frequently try to prove it is true for all n using induction. So, if that's true for all values of n, this is the proposition. N was 100 in that simple example. We went from 1 to 100, and then n was 100. This would be 101 over 2. So we're going to prove that it's true for all natural numbers n. So if you would like, this is your proposition n. This is just the definition of summation. This and this. This means sum up all the numbers I going from 1 to n. That's this. Here's the formula we're going to prove. You could say this is equal to this, or this is equal to this, whichever way you prefer. Before I start the proof, though, I'm going to go over what frequently causes some students difficulty. And it's one of the more simple parts, actually. So let's make sure we get this down right. We could call this Pn. And we want to prove that that statement is true for all values of n, all the natural numbers n. Well, if that's true, we need to be able to figure out what the next proposition would be. Proposition n plus 1. So if that's Pn, what would Pn plus 1 be? Well, you basically replace n with n plus 1. And it would go 1 plus 2 plus, I'll go ahead and put the plus in, but you have to go one further there. And what are we trying to prove? If we assume that Pn is true, and we want to prove that Pn plus 1 is true, we have to be able to state what Pn plus 1 is. according to this, what should this sum be right here? Well, notice we're summing to n. There's an n here and an n plus 1 here over 2. Well, here we're going up to n plus 1. So that n is going to become n plus 1. That n is going to become n plus 1, which another plus 1 gives you n plus 2 over 2. So make sure you understand that, how to come up with a proposition n plus 1 if you're given a proposition n. Okay, I'm going to erase this, but we'll end up putting up something like it on the board in just a few minutes. All right, well, principle of mathematical induction, or weak induction, says you first have to do a base case, which if you're trying to prove, I guess I left off part of this statement. Prove this is true for all natural numbers n. That's the key. It says this is good, mathematical induction is a good way to prove it. It's a statement true for all n. So the first thing you do is just show that it works for the base case, n equals 1. So that would simply be, what would this be if n is equal to 1? Well, if n is equal to 1, there's only one element. You're really not having to sum anything, but the summation symbol, if I goes from 1 to 1, of I is just the number 1. So 1 equals, and I'm going to put a question mark. Sometimes I'll put a question mark on here, acting like we know it. We don't know it's true. We're going to prove it's true. 1 equals, and the right-hand side would be 1 over 1 times 1 plus 1 over 2. And that number here is 1 times 2, 2 over 2. It works. 1 is equal to 1. Now here's where the tougher part comes in. Maybe I'll go to the right here rather than underneath. We need to prove that pk implies pk plus 1 for some arbitrary natural number k. So we're going to assume it's true for some k and then prove it's true for k plus 1. And if you use n and n plus 1 here, I have no problem with that either. So you'd be assuming that's true. Well, how do we prove this? Well, if we assume this is true, we'll say if pk is true, if 1 plus 2 plus all the way up to k is equal to k plus 1 over 2. That's what you get when you plug the variable k in place for n. So we're going to assume that that's true. And we're going to have to prove then that it works for pk plus 1. Then, and this would be pk plus 1. I equals 1 to k plus 1, which is, and I'm writing out maybe more than I need to. I'm going to go ahead and write this 1 plus 2 plus up to k plus 1 is equal to, and here's where we use, this is called the induction hypothesis. We're assuming this statement is true. And let's use that fact right now. If that's true, well, what is this right here? This portion of it, I know what it is. This right here is equal to k plus 1 over 2. So, by the induction hypothesis, I know that this is equal to k plus 1 over 2 plus k plus 1. I just used the inductive hypothesis, or the inductive assumption, assuming this is true, which is called pk, and this would be pk plus 1. And let's do some algebra on this. Maybe I'll go to the right one more, just to save some room. I'm going to get a common denominator, plus multiply this by 2 over 2, and I get 2k plus 1 over 2. Okay, so if we factor out the k plus 1, actually let's factor out the k plus 1 over 2 out of both of those terms. And what would I get? K plus 1 over 2, I would get times k plus 2, which can be written k plus 1, k plus 2 over 2. Exactly what we wanted to get. That's the end of the proof. We did the base case, k equals 1, and we proved then that if pk is true, then pk plus 1 is true as well. Okay, let's go to the next one. We're going to prove this. Oh, I guess I left off again. For all natural numbers n. Well, let's just dive in and do the base case. The base case will be k equals 1. N equals 1. Yeah, for the base case, we'll just say n equals 1. All right, if n equals 1, then this is just going from 1 to 1. So I is going to be a 1. So the entire left-hand side is 1 times 3 times 1 plus 1. And that would give us 1 times 4, 4. And that's equal to, well, I'm going to put, is that equal to, question mark, if n is a 1, it's 1 times 1 plus 1 squared. That gives us, in other words, 4 equals 1 times 2 squared, 4. Base case works just fine, as expected. Now for the second part, we're going to do the I'll put a question mark here. Does pk imply pk plus 1? Well, let's find out. If it is true, if this is true for some arbitrary natural number k, if I equals 1 to k of I 3i plus 1 equals k times k plus 1 squared, then now we need to look at what the left-hand side is when we go up to k plus 1. Then I equals 1 to k plus 1 of I 3i plus 1 is equal to going from I to k plus the k plus first term. So maybe I'll, let's see, do I have to write out every baby step? Should I? No, I'm not going to. Let's write out what this sum is. Okay. And what will I have to add to this? If I'm saying take this expression and sum it from 1 to k plus 1 is equal to this exact same expression going from 1 to k, I'm only missing what happens when I is a k plus 1. So the k plus first case is going to be k plus 1 times 3 times k plus 1 plus 1. All I did in this expression, or this expression, or this expression, is we already went from I being 1 to k. Now I need to replace I over here with k plus 1. So that I became k plus 1 times 3 times k plus 1 plus 1. That's exactly what I have here. And before I continue simplifying, I'm going to make a note. I usually do this when I do proofs by induction. Where do I need to end up? I need to end up by showing that this is equal to this expression only having k replaced with k plus 1. So I'm going to end up with, I'm just going to write it on my scratch paper over here. That's what I need to end up with. So I just need to show that this expression is equal to that expression. Okay, well, by the inductive hypothesis or induction hypothesis or assumption, I know what this is. If this is equal to that, so that's just k, I'm going to go to the right. K plus 1 squared plus k plus 1, and this would be what? 3k plus 3 plus 1, so 3k plus 4. All right, and I know we need to end up there, and I think we're almost done. Let's factor out a k plus 1. Factor out that and that. And I'll still be left with a k plus 1. I'll be left with k plus 1 there. This times this gives me that. Plus 3k plus 4. Which is equal to k plus 1 times k squared plus k plus 3k plus 4. That's k squared plus 4k plus 4, which is a perfect square. K squared plus 4k plus 4 is k plus 2 squared. Exactly where we needed to get. So we started by proving the base case, and then we assumed that pk plus 1 implies pk being true implies pk plus 1 is true.